break, so because now we need to move to the next talk. So the next talk will be by Vitaly Neustroev from the University of Oulu, which is treasure chest of period bouncers, detection of the brown dwarf donor, or in BW Sculptoris, I think. So do you want to start your presentation, yes. Vitaly?
Yep. Do you hear me?
Yes.
Okay. First of all, I would like to say thank you for
the but we are not seeing your slides, so okay.
Or
at least I'm not seeing them. Wait.
It's strange because I just wait a second.
Maybe it was just me.
I can't see them.
Okay.
Do we see it now?
No, I'm seeing now. Yes, now I see it. Perfect. So please.
Okay, great. Okay, so first of all, thank you for this opportunity to give a talk. And this work began as a master thesis project of Ike Martinen, my student at that time. Now Ike is a PhD student in University of Turku and working on supernova. And so during his work, we found quite a lot of interesting things in this object. So we decided to return to this object later again to look at this in more detail. And so I would like to present these results. Okay, so first of all, what are period bouncers and what treasures do they hide in their chests? First of all, period bouncers are accreting white dwarfs, or we call them cataclysmic variables, at the very late stage of the evolution. The biggest problem is that it's expected to be a lot of such objects, but known just a few of them. And this is a major challenge to our understanding of cataclysmic variable evolution. So it's quite important to study these objects. Then donor stars in these objects are evolved to kind of brown dwarf-like objects. Interesting thing is that these donors were not brown dwarf from the beginning. Originally, they were just man-sequence stars. So it's not obvious that now these brown dwarfs behave like ordinary brown dwarfs. So it's interesting to try to find a difference between what we have in period bouncers and in just normal brown dwarfs. Then another interesting thing is that in period bouncers, we have a very low mass transfer rate. So the properties of accretion disk in binaries with low mass ratio and low accretion rate are quite poorly understood. So it's also quite interesting to study these objects. So then, okay, why BW Sculptoris? First of all, this is a solid period bounce candidate. It's known already quite a long time. And Taichi Kata, in particular, estimated a mass ratio in this object using his method based on superharms, and it's quite low, and it definitely should be a period bouncer, but no dynamical evidence were presented yet. Then the orbital period of BW SCL is 78 minutes. On this slide, you see that when the object's cataclysmic variables evolve from longer periods to shorter periods, when the donor star becomes a brown dwarf, then the direction of period changes. So we should have we should have a period minimum, after which the period will increase again. The exact value for this period minimum is not yet known. We have some theoretical predictions for it. And from observations, McAllister obtained that the period minimum should be about 79.6 minutes, but with some quite widespread around this value. So what we see here in BW Sculptoris, we have that it sits almost exactly at the period minimum. Then possibly one of the most important properties of this object, it's one of the brightest period bonds candidates. So because it's bright, we can observe it with many instruments, and we can obtain its parameters quite accurately. Another interesting thing that this object had super outburst in 2011, already quite a long time ago. So it was enough time for white dwarf to cool down after the outburst. And also it was not so long time ago that these objects could be observed before the super outburst. Indeed, this object is quite easily accessible with ESO telescopes, and we found that there exists archival data obtained with these two instruments well before the super outburst. So we performed our new observations in 2017 and 2018. We used a smaller telescope, NTT telescope. We observed it in optical and in infrared. We obtained spectroscopy and photometry in all filters. Then we also observed it with Swift XRT and the ultraviolet optical telescope using all bands. But as I said, the best data are available in the ESO archive. Two observations obtained with the O-MESS spectrograph, and one great data set was obtained with X-Shooter in 2010, just before super outburst. So it was very close to super outburst, just 1 year before it. And also this object was observed with TESS. What I would like to say that from this plot of the light curve, we see that the object was extremely stable on a long time term. It was almost always about 6.5 magnitude. Then it experienced the super outburst, and since then, now it's again stable, but the object didn't reach the pre-outburst level. As we found in this work, one of the reasons is that it seems that the white dwarf now is a little bit still hotter than it was before, but the reason for it, most likely, that it seems that the mass transfer rate a little bit increased. We see that the accretion disk now is a little bit brighter than it was before the super outburst. I will show it later. Okay, so as I said, the base data set which we have, this is the X-Shooter spectra, and I show this is the average spectrum. The great thing is that the exposure times of these observations were just 1 minute. So it's extremely high time resolution. 239 spectra were obtained. It covered more than 4 orbital periods, and signal to noise ratio of the average spectrum is extremely high. It's few hundreds. So you can see it. So first of all, what we see, broad white dwarf absorption lines, and then emission lines sitting inside of white dwarf lines. The gallium lines are very weak. I will discuss it later. And there's one unfortunate thing is that because of very short exposure time, this near infrared spectra are not so good as other spectra in optical and ultraviolet wavelength ranges. So they are very noisy, and actually this average spectrum is heavily smoothed. Still, we see some lines here, for example, gallium line and hydrogen lines. Well, if we will go to trail spectra, we will see much more detail in this spectra. And let me, first of all, look how different these trail spectra are in different lines. In particular, we detected silicon line here. Then we detected magnesium-2 line from the white dwarf, and actually also from calcium-2. Then we have quite normal hydrogen lines from the accretion disk with normal S wave from the hotspot, but then we see additionally one additional S wave. So if we will look at this line in more detail, then magnesium line is sitting closely to gallium line 4471. And what is interesting, gallium line doesn't show any sign of the accretion disk. So it's just one hotspot. And from magnesium-2 line, we see that actually it's a little bit wobbling. So it shows a sine wave here, so which we will use to measure its radial velocity. Most interesting is the H alpha line. So in this color form, it's possibly a little bit better. What interesting here, that this S wave, the second S wave, has a smaller amplitude of modulations. It disappears at half the orbital period, and it strongly indicates that it's originated on the inner hemisphere of the donor star. And indeed, if you will look at other hydrogen lines, so they show normal S waves, and this is the silicon line, shows the donor line, which phase is a little bit shifted, as you can see. So we detected these lines from the donor in quite many spectral lines, including iron 1, calcium 2, and later, when we calculated Doppler tomograms, we obtained these pictures. So it's very nice detection of the donor in this object. What is interesting and what is very unusual in this case, the object now is already many years in quiescence, and usually we don't see the lines, the irradiated lines from the donor during quiescent state. Usually we see them only, say, during outbursts or during the declining stage. Now it's definitely already quiescence, but we still able to see these lines on the inner sphere of the donor star. What I would like to add to it, that in fact, it's the great quality of X-shooter data allowed to see it. We don't see these lines in even higher resolution spectra obtained with O-MESS because the quality of those spectra are much lower than of X-shooter. And we don't see these lines in the EFOSC and in NTT EFOSC spectra because the spectral resolution is much lower there. So X-shooter allowed to see all these details. Then again, one more thing is that gallium lines, all gallium lines, don't show any sign for the accretion disk. And again, when we calculated Doppler tomograms, and interesting thing I forgot to say, that we even see a hotspot even from gallium-2 line. It's definitely detected, but we see no accretion disk, and we see no sign of the accretion disk in tomograms. I will return back to Doppler tomography later, but now let's try to determine the system parameters of this object using the lines which we detected. So using a set of lines, it's listed here, these lines, we obtained the semi-amplitude radial velocity modulations for almost 400 kilometers per second. Then, because these lines appeared not, they didn't come from the full star, they come only from the half of the star, from the inner part of it. So we have to correct it. We corrected this value, so we obtained this one. I have no time to discuss it in detail. We can discuss it later. Then we obtained the systemic velocity, gamma velocity. So this is from the lines from the donor star. Then using magnesium 2 line, we also were able to obtain the semi-amplitude radial velocity. Then we found the average radial velocity of this line, which in fact is a sum of the systemic velocity. Yes? Sorry?
5 minutes.
Oh, it's okay. Because it's a sum of gamma velocity and gravitational redshift. So we were able to determine the gravitational velocity. Then we also additionally were able to find the rotation velocity from this line. And well, just I will summarize that the final system parameters are listed here. So what we found that it's here quite massive white dwarf, about 0.9 solar masses. Very low mass brown dwarf, 0.05 solar masses. And the inclination angle is just below to be this system eclipsed. Unfortunately, we don't have eclipses here. So this is the parameters, and so we find solid evidence that this object is indeed brown dwarf in this star. Well, then I now switch to properties of the spectral energy distribution and accretion disk spectrum. So we fitted the ultraviolets, the blue optical spectrum with white dwarf models. We obtained independently that log G is equal 8.5, consistent with what I just told you before. The temperature of this object is about 14,750 Kelvin. This is also consistent with the results obtained previously in the literature. Then we have a very broad spectral energy distribution. We combined all available ultraviolet and infrared data up to quite long wavelengths. So we then can remove the white dwarf spectrum from the observed spectral energy distribution and to obtain the spectrum, which is the sum of the accretion disk and donor star. But if the donor star is still visible, then here I plotted two spectral energy distributions of donor stars according to the models by Christian Knigge for the given orbital period, if the object is still on main sequence or if this object is already brown dwarf. So what we see that if it's normal star, then we definitely will see some harm here in the spectral energy distribution. We see nothing. And for his prediction was the brown dwarf of the temperature about 1400 Kelvin. Well, to be on the conservative side, taking into account quite noisy spectra, we put the limit about for the temperature of the brown dwarf below than 1600 Kelvin. And then using this spectrum, we can calculate some parameters. So in particular, we found the luminosity of the accretion disk is quite low. We can compare it with the luminosity with X-ray luminosity, which we obtained from X-ray observations. You see it's quite larger than in X-rays. So the accretion rate is very low. And interesting thing that if we will calculate formally the effective temperature for the accretion disk, we will obtain just 2000 Kelvin. So, well, it's then definitely indicate the possibly whole disk from the inner edge to the outer edge, the disk is optically thin. Well, and then now a few words about Doppler tomography. Well, the data allows to get extremely good quality Doppler tomograms like here, but what is interesting, is that if you will use all this data, the data will not be...
One more minute.
Okay, so I'm finishing, it's just a couple of slides. So we don't see the donor star in the reconstructed spectrum. Why? Because the feature is visible only during half of the orbital period and disappears during another half. So it violates an assumption of Doppler tomography that during all time, all points should be visible equally. But if we will take only part of the spectra, which is more than enough to calculate the Doppler tomography, we will reconstruct it. You see now the Doppler, donor star. Similar situation we see in gallium lines. In gallium lines, we see very strange things. I have no time to describe it now, but we have the splitting of the S wave and the appearance of the shadow in the S wave. Here, again, they are not reconstructed in the average spectrum. But if we will do the same, select only part of spectra, we will reconstruct, and the shadow is here, the splitting is here. But you see how the hotspot has changed. It means that the hotspot is visible very differently when we're looking at the system from different sides. So now I calculated a kind of dynamical Doppler tomography when we used a part of spectra centered on different phases, and you can see how different the hotspot is in these maps. Okay, so then my conclusion is that this object is a confirmed period bouncer with quite low mass. White dwarf is quite massive there. Accretion disk is optically thin, and hotspot is optically thick. So that's it. Thank you.
Okay, thank you very much for this work. Very interesting. Very interesting. So we have time for questions. We have some time for questions. Yes. So please, someone raising the hand. Oh yes, please. Klaus, do you want to make your question?
Yes. Can you hear me?
Yes, perfect.
Okay. Okay, Vitaly, very interesting work, very careful, very nice. You probably know that the source, that the star is an X-ray source.
Sorry, I don't hear you very well. So please repeat again.
Okay, let me see.
It's the sound is not very clear from you.
Yeah. Is it better now?
Yeah, it's much better. Yes, please.
Okay, Vitaly, thank you very much. Very interesting talk. Very nice work. You probably know that the star or the system is an X-ray source.
Yes, it's an X-ray source. Yes.
What is are the X-rays coming from? What is the idea?
Well, generally the idea is that it's coming from kind of boundary layer. So, well, because the disk is not optically thick, so it's not it looks like the boundary layer is also not optically thick, but as we see, the luminosities in optical and in X-rays is very much different, and we already saw it in other objects. So in principle, it's quite, we can explain it quite easily because the system now is in quiescence. So the mass transfer rate is very slow, and it becomes slower then closer to the white dwarf. So we don't have enough mass there to create significant X-ray emission.
Okay, so I see
Thank
that
you.
we have a couple of questions, but we don't have so much more time, but we will have the coffee break. So I urge those who wants to ask questions to Vitaly to go to the coffee break, but we still have time for one more question. So I will ask Harvey Richer whether he wants to ask the question, because I saw he was the first one to raise a hand. So
Yes, thank you. Very nice talk. I'm interested in the secondary here. You keep calling it a brown dwarf.
Yes.
And it's true, its mass is below the hydrogen burning limit. But in the past, this star burned hydrogen. So we can anticipate that its structure is not exactly the same as a brown dwarf. And so is it appropriate to use a brown dwarf model to characterize this star where its structure could be quite different than a normal brown dwarf?
Well, yes, I definitely agree with you. As I told you in the very beginning, it's different brown dwarf than what we can have as normal brown dwarf. But we cannot say how it's different. What actually we should do now, we should extract a real donor spectrum in infrared and compare it with normal brown dwarfs to see what is the difference. So, well, for now, we call it brown dwarf-like objects. But yes, okay, I completely agree. I cannot say that it shares the properties with normal brown dwarfs. Yes, I agree with you.
Marcelo, you're muted.
Is it Tom? Did you say something?
Marcelo, you're muted.
it's happening to me all the time, so sorry. Yes, so thank you very much for this second presentation. Now I will open the breakout rooms, and Vitaly will put you in room 2 and Lisa in room 1. And I mean, you can move yourselves also, but if you cannot, then ask me and I will just move you to the breakout room. So